Okay, so when talking about set notation, like what are the most common sets that you're going to deal with? Well, let's talk about the first one, the big one. Let's just say R. Okay, this is going to be the set of all real numbers. All right. And so what can we say about the set of all real numbers? Well, what we can say is, one, that it's continuous. Okay. And so what do we mean by a set being continuous? Okay. If you have, all right, this class is discrete math. So a big concept in discrete math is the difference between the continuous and the discrete. Okay. So if we talk about the set of all real numbers, we can't divide the set of all real numbers into a discrete sequence. Meaning, all right, if you think about, all right, if you have 1/2 and 1/4, you can always find numbers in between there. And it doesn't matter how you divide, you can always find one number that is in between the two numbers that you're talking about, okay? So that is what is actually meant by this continuous. And not only is the set of real numbers continuous, there's another quality about it that we'll talk about. This is also this is uncountably infinite. Okay? Now, what is meant by uncountably infinite, now there are some different definitions that will show up. One definition that shows up is that it has a mapping with the natural numbers. Okay? And actually, y'all's book doesn't even use the phrase natural numbers because there's too much discrepancy between different definitions of what a natural number is. Some include zeros, some don't. So we'll just say if you can map it to the, let's say, integers, okay? And so the next set that we're going to talk about, so that's the set of all real numbers. Now, let's look at a discrete set. And so let's say the integers.
That's a Z, right?
That's a Z, yes. And common notation for it is just that Z with a bar. Okay. And normally when in these generic sets, they always include this extra like little bar right here to distinguish it between just a normal Z. Okay. Now the set of integers, and we will call this. All right. So the set of reals is between negative infinity and infinity. This is also between negative infinity and infinity. But if I go backwards, this would be -3, -2, -1, 0, 1, 2, 3, and then going all the way off to infinity. Okay? Now, this set is not continuous. I'll give everybody a second to write that down. Okay, so instead of being continuous, this set right here is discrete. Okay. And this is countably infinite. All right. Okay, now, what makes this one discrete versus the other one being continuous is that you can find space between any of the components of this. Okay, so they're discretely separated from each other. So between -3 and -2, there's obviously a lot of space. But even if you talk about the set between 0 and 1, I mean, if you start talking about, well, what's 1 billionth and, I don't know, 2 billion. Well, you can find a number 0.5 billion between there. So there's, I mean, 1.5 billion between there. So you can always find something smaller, but these guys are discretely separated from each other. That's the main difference between something that is discrete and something that is continuous. Okay. There are some rather bizarre ones out there. Let's say we looked at the set of rationals. Okay. Okay. And so what is meant by the set of rational numbers is numbers that can be represented by fractions. A little bit off the screen. Okay. So the set of rational numbers, when you really get into some of the deeper levels of math, this is a very interesting set to deal with. Okay? So any numbers that can be represented by fractions. This is also continuous, technically. Okay, so if you think about this, when you talk about rational numbers, if you are saying, okay, 1/2 and 3/4, you can always find a fraction in between that, and you can always keep subdividing intervals until you can find a fraction in between a fraction. I mean, that's always possible to find a fraction in between a fraction. So that's what makes the set of rational numbers actually continuous, because you can always find another fraction in between a fraction. And you can keep subdividing intervals, and no matter what, you can always find something in between it, so there's not a discrete amount of distance in between any fraction, okay? What's interesting about the set of rational numbers is that this is a continuous set. But when we talk about, is it infinite or countable, the set of rationals is actually and we'll spend more time talking about this later. But when it comes to set theory, you end up with these very strange qualities of something it's continuous, but it's countably infinite, okay? Now, if the set of rational numbers is continuous and countably infinite, but the set of reals is continuous and uncountably infinite, well, then what does that tell us about irrational numbers? It means that the irrational numbers are actually uncountably infinite, meaning they're more irrational numbers than rational numbers, which seems almost counterintuitive, because the numbers that we come around in our daily lives are always represented by fractions, but what normally, and so what other numbers out there could represent all this uncountably infinite numbers of this set of real numbers? I mean, does anybody have an example of an irrational number? Pi. Yes, thank you. Well, I mean, some of the more classic ones are pi, if you think about the square root of 2, or phi, the golden ratio, things like that. Those are the really celebrated irrational numbers. But yeah, there's way more irrational numbers than rational numbers. And so it seems counterintuitive because that's not the numbers that we normally come into in our daily lives. But they're very special numbers in themselves. Okay. Another one that we have a tendency to run into, or that we use a lot, is instead of just writing it as the integers, a lot of times we'll write it as z plus, and that will be the positive integers. And so that would be the set so we're starting at 1 and counting all the way up to infinity. And so this one is discrete. And countably infinite. Okay, and normally our counting systems will start off, a lot of times they actually start off with 0. And so you can include that in there. And that's where there's kind of this discrepancy between the natural numbers and if we just say the positive integers. And you will come across multiple definitions. And actually in y'all's book it says we are not going to use the phrase natural numbers. But with normal counting systems, especially when y'all get into calculus 2 and things like that, and we'll talk about infinite series. When I talk about infinite series involving geometric series, I basically tell my students every time, you have to begin at 0. So there's a little bit of discrepancy, but there's a way to actually alter the formula for geometric series to make them begin at 1. And it's not my favorite formulation of it, but some people do that. Okay. Now, let's talk about which is a subset of which. Okay? So, A is a subset of B. This literally translates to A is a subset This is true if and only if every element of A is an element of B. We'll talk about proper subsets right after this. So, let's look at the sets we were just looking at a second ago. And so if I was considering the subsets of the sets that we were just talking about, well, the set of positive integers would have to be a subset of the integers. Okay? So, I mean, because every positive integer is an integer, so every element in Z plus is in Z. And so the set of integers is a subset of the rationals. Okay, because if you think about any number that can be represented by a fraction, well, what's 3 represented as a fraction? It's 3 divided by 1. That's still 2 integers representing a fraction. So the integers are, in fact, a subset of the rational numbers because every integer can be divided by 1. Okay? And so what would be a subset of the rationals? I mean, what is bigger than the rationals? That would be the reals. Because the set of all real numbers would contain the rationals, the integers, and the reals also contain the irrational. Okay? And so we can actually think of a set that is even bigger than the set of the reals. Like, what is a set that would actually be bigger than all of the reals? I mean, there are infinitely many of them, but a very common one would be actually this. Okay. So the positive integers are a subset of all of the integers. Okay? All of these integers are a subset of all of the rational numbers. Okay? And then the rational numbers are a subset of the reals because the real numbers contain both the rational and the irrational. Okay? And then why would the real numbers be a subset of the complex numbers? Is because we're adding an extra layer of complexity to it, meaning that the complex numbers contain the real numbers and the imaginary numbers. So when you actually plot out the complex numbers, so when we look at C, we have an axis, and we're going to be going over ordered pairs also today. And so this line right here is the real numbers, and this line up here is the imaginary numbers. We'll do a proper subset too. So, because the complex numbers contain the entire real axis and any imaginary, and if y'all are familiar with what imaginary numbers are, it's the square root of -1. Which historically, from mathematicians' standpoint, were thrown out quite a bit as not being useful. But the fact of the matter is, going into the complex plane is one mathematician put it as the shortest distance between a problem and a solution passes through the complex plane, because there are a lot of problems that can pass through the complex plane that become very simple as long as you know how to manipulate it correctly. Yep. You know what? I'm going to stop the video at that point right there.